Here is Professor Joachim Kunert from the University of Dortmund. He's going to talk about optimal block designs for comparison with the control in the presence of correlated errors.
Good morning. Is this on? Do you hear me?
I think so. The red line is on.
Okay. I could have made my title even a bit longer because I should have added for short block sizes and for enormously many blocks. And this is joint work with Richard Martin and with John Eccleston. So I considered a simple block model, and I have T+1 treatments and one design, which gives one treatment to each of the plots in each block. And so the model has, it's not really, oh yeah. The model has treatment effects and has block effects, and we have a treatment design matrix which is influenced by the design and the block design matrix. And what we assume for this is that the errors within blocks are correlated and between blocks are uncorrelated. And the covariance structure for the correlation within the errors within the blocks is the AR1 process. So we have a stationary process, and it depends on just one parameter. And we assume that this parameter is known. So we can do the weighted least squares analysis. And we are interested in comparing the effect of the t-test treatments with the control treatment 0. So, and the variance of such a comparison is this expression here, which depends on the information matrix, on the inverse of the information matrix, the generalized inverse of the information matrix. And the information matrix is calculated with the help of the block design matrix, of the covariance, and of the treatment design matrix. No, keep on forgetting. So we are interested in comparison of treatment effects with the control, and we want to estimate the average variance of these comparisons. And this criterion here is convex. Therefore, it performs worse than the criterion of a virtual design we might construct from our design by making it symmetric. So this is the original information matrix. We multiplied to the left and right by permutation matrices which come from permuting the test treatments, and then we average. So this, in general, this will be a non-existing design. If you have very many blocks, then you can actually derive this design. And we can then calculate a lower bound for the criterion, for the A criterion, which depends on the information, on the eigenvalues from the virtual design. And it has two different eigenvalues only. And but these eigenvalues can be calculated from the original design directly. So we get a lower bound for the A criterion, which is valid for any design, and usually is smaller than what we actually can get. And what we try to do is to minimize this lower bound. And the nice thing is that each of these two parameters that we have, which we try to minimize, which we have for the function that we try to minimize, is linear in the single blocks. So we can calculate this parameter for the whole design by calculating the corresponding thing for each single block and then taking the convex combination of them. However, the bound that we actually want to minimize is not linear because it's a nonlinear function of these two parameters. And we realized that that's the same situation that we usually have in crossover designs. In crossover designs, we have the problem that we want to minimize a function which is nonlinear function of something that's linear in a single blocks. And there was a method developed by Kushner in 1997 which proved to be very helpful for optimizing crossover designs. And so we thought, why not try to apply this method to our situation here on a simple block model. So that's what we try to do. So the first step is instead of minimizing the criterion we actually want to minimize, we maximize the inverse, 1 over the criterion. So that's an easy step. And now, the interesting point with the Kushner method is that instead of minimizing the QD, this thing here, he introduces a function, a polynomial, a quadratic function, and we find that this quadratic function has its minimum at this point, and the minimum of the function is exactly the thing that we want to maximize. So instead of maximizing the QD directly, we introduce a function and try to maximize the minimum of this function, which seems weird, making life more complicated, but it's actually helpful. The advantage is that this function here, this function is linear in the blocks. So we can write it as a convex combination of the function of the blocks. And here is Kushner's method. We have to look all possible blocks, and we have to look at the maximum over the functions for all possible blocks, and then find the minimum. And this is an upper bound for the thing that we actually want to maximize. You can see here the situation when we have only 2 possible blocks. Then this is the function for the first block, this is the function for the second block, and any design that we have will have combinations between these two kinds of blocks. So the function for the whole design must be between these two, because it's a linear combination. And because it's between these two, the best thing you can get is that it's between these two and has its minimum exactly here at the minimal has its minimum at this minimal point of the maxima. And to get this, you have to take a combination where you take the proportions of the two in such a way that the derivative is 0 at this point. At a situation like this one here, you have the minimum of the maxima here, and then you can get an optimum design which consists of just one kind of blocks. One thing else, I forgot to mention, if you have any kind of block where the polynomial always stays underneath these two, you can forget about these kinds of blocks. Because you want to find the maximum of all possible sequences and then the minimum of the maximum. And this way we could kick out quite a few possible candidates for blocks. We could find that we can restrict our attention to sequences which are binary in the test treatments. Each of the test treatments may appear once or not at all, but not more than once. And we could also see that we can kick out any sequence which has more than half of its plots filled with the control treatment. And now I come to the small number of blocks. We only consider two cases. The first one is 3 plots per block, and the other one is 4 plots per block. And if we have 3 plots per block, any sequence which leaves the position of the 0 constant but relabels the names of the controls will lead to the same parameters m1 and m2. so we call any of these sequences equivalent. They are also equivalent if we simply reverse the order. Instead of reading from the beginning to the end, we read from the end to the beginning. And this means that we have 11 possible sequences to consider for this situation here, with 3 or more control treatments and p equals 3. And with the two easy results, we could reduce this to 3. And these 3 are the following. We have either the control is on the edge, or it's in the middle, or there's no control there at all. Sequences with 2 controls can be kicked out. And now we have the polynomials for these 3 sequences, and what we have to do then is to look at these 3 polynomials and find the maximum of these 3 and find the minimum of these 3 over x. And you see that you get a different situation for each value of t, and you get a different situation for each value of lambda. And so it's a very easy task, but it's a lot of different cases to consider. And due to the fact that lambda is between 0 and 1 and a continuous function, you have more situations than you can count. What we did when we analyzed this function, we found that we only need 2 sequences of the 3, as if we restrict to the case that the correlation coefficient is positive. We need the one with the control in the middle with a proportion 1 minus p, and we need some which do not have the control in it at all. And this proportion, of course, depends on the correlation coefficient and on the number of test treatments. And here's the proportion of, if we start with the case that we have 3 test treatments, with this the correlation coefficient. When the correlation coefficient is small, less than 0.2, we only need sequences which have the control treatment in it. But if the correlation gets larger, then we may need some sequences which do not have the control treatment in it. And when the number of control treatments gets larger, we need more and start earlier with blocks that do not have the control treatment. And this goes on. When we have 5 control treatments, we will always, even for a correlation of 0, need some blocks which do not have the control treatment in it. And with 25, we need quite a few, which is quite plausible, because if we have the control in each block, then they will appear much more often than any of the other treatments. Here's the case that we have 4 plots per block and more than 4 or more control treatments. Here we had 32 non-equivalent sequences to begin with, and with results 1 and 2, we could reduce this to 6 at least. So, and these are the ones that we're interested in. We have some with 2 appearances of the control treatment, and we have some with 1 appearance, and we have the possibility there's none. The ones with 3 are kicked out by result 2. Would be too many. And now looking at the polynomials, I don't give you the formula for all of these. We find that if the number of treatments of the control treatments is more than 6, we need some blocks which have 1 control treatment in it and some which don't have them. And the proportion depends on the correlation coefficient lambda, like we had in the case of block size 3. And you see if t is equal to 6, we get a long time, we get along without any control, without any block that does not have the control. And for large correlations, we need some. And if the number of blocks gets larger, we need more. If we have 10 control treatments, we have to start even at 0 with some blocks that do not have the control treatment in it. And with 25, you need quite a few. Now this seems to be rather boring, so there's two cases which I found exciting. At least I find exciting because I don't understand them. If we have 5 treatments, for t equals 5, we have, for large correlations, we need some blocks which do not have the control in it, and we need some blocks which have the control in it. And if correlation goes down, then we need no blocks which have no control in it. And I made a new graph in which this axis is extended so we can see these two bits a bit more. Now when the correlation gets even lower, the number of control treatments seems to be too small. So we need some blocks which even have 2 control treatments in it. And so it starts around here at 0.8 correlation. And when the correlation gets lower, then the proportion of 0 has to be even more. And at this point here is where I start to not understand what's going on, because when the correlation now gets lower again, it suddenly disappears. We suddenly don't need so many zeros anymore and have blocks with just 1 0 in there. And we have no intuitive explanation for that. And if the number of treatments is 4, we sort of have this plot here extended. So we have sequence with 1 0 and sequences with 2 zeros in it. The proportion increases when lambda gets smaller, but for very small lambda it goes down again. When I rehearsed this yesterday, it took me 5 minutes longer, so I kicked out some slides, which I now realize I could have kept in there. The problem with these designs, of course, is that these designs maximize an upper bound, and you can't actually achieve this upper bound for 2 reasons. And the first reason is you have a continuous function for the proportions. So for most lambda, the proportion will be an irrational number. So you need infinitely many to get the right proportions. And the second problem is you only achieve this upper bound if you have a symmetric design. If you have this virtual D bar design, which you can only achieve in reality if you permute every block very many times. So you need, in order to get these design, you need an enormous amount of blocks, even if this fraction happens to be rational, like in the case when you only need 1 sequence. Even in that case, you will need quite a few blocks, which is too large for any realistic case in reality. But there's still some use in these designs because, there's still some use in these designs because what we do get is an upper bound for the criterion. And so for a given design which does exist in reality, we can compare its A criterion to the bound and then see how efficient it is. And if we're lucky, it's highly efficient. And we found some cases where our designs were reasonably efficient. And this was on the slide that's disappeared. And just to give you a few references, there were some early papers in the early 90s which dealt with the same problem that we are dealing with. And then things came to a stop, and then Kushner's wonderful paper appeared, which we think helps a lot to get some progress, even for the simple block model. Thank you very much for your attention.
Questions or comments?
Could you just go back so that we can see some sequences? Oh yeah, that'll do. For example, when you write 1023,
Yeah.
if I turn that back to front and get 3201, you're counting that as equivalent.
Yeah.
So that's why you don't bother to show it.
Yeah. Yeah.
So is your equivalence up to permuting non-control treatments and reflecting the sequence back to front?
It's up to relabeling non-control treatments and reading backwards up to front.
Okay, thanks.
These are the two. And this reduces the possible sequences largely, but it goes down to in the grammar. Somehow I lost the number. So it goes down to 32 possibilities for t equals for p equals 4.
And then those two simple results cut that down.
Yeah, and they
those
cut
steps.
them down to 6,
Yeah.
which is. But for 5, we didn't even try to.
Questions?
In those unusual cases, the pi was always small, less
Yeah.
than 5%.
Yeah.
So
I think a design which does not use them will be very efficient, yes. But it's still, I don't understand why it happens, so that's the point. This seemed to be quite easy. You need more controls if lambda increases, and you need less controls when lambda increases, and you need less controls when t increases. But somehow these little unusual cases don't fit into this scheme.
I was just wondering what happens if you have block size of 2. Probably everything is quite easy.
Yeah, with block size of 2, the correlation plays no role. So you're in the uncorrelated case, because we have fixed block effects. I didn't mention that. So by subtracting the fixed block effect, the correlation disappears.
Other questions? Now let's thank Joe again.
So I gave you 5 minutes break now.